so that the meeting is recorded. Okay, got it. So thank you everyone for coming. Thank you for to Antalfa for this opportunity and to have created this hacker house in Chiang Mai that we love and bringing here like the best of the best in the ZKP community. I'm very excited to have the opportunity to present this thing that I've built in the residency in Vietnam, just like last month. I've been working on this, so really excited. So first, perhaps a bit about about me. I forgot to put me there. A bit about me. To kind of introduce me, I have 20 years of experience in software engineering, embedded and distributed system. I graduated first class in computer science at Bath. Then I worked for ARM, the microprocessor designer on subjects of server software on the ARM architecture. When like more than 10 years ago. In 2010, when there's still like kind of like ARM servers were an idea only and the imagination of the ARM people. And then I was like porting server software to ARM and running server software on ARM. Then I co-founded a startup, Uniplaces, that is now in 9 countries, and I exited after kind of creating from the ground up with other co-founders. It's not very technical, so I guess it's not very interesting to you, but it's kind of a B2C platform, but kind of like that gave me more experience in entrepreneurship and kind of launching my own projects, etc. And then it seems kind of like, I mean, I was kind of interested in blockchain for a long time ago, but kind of in 2021, I decided I want to switch to work full time in blockchain. Then the first opportunity came, I joined Gitcoin kernel. That is an awesome community. I met awesome people there and had also experience. And since then, everyone, we go to a conference, there is like kernel people there, and it's a great community. I recommend it to anyone to apply, anyone that is interested into getting into blockchain, and you get to meet all sort of people from all sort of backgrounds that kind of kernel put together, and there is like this 2-month kind of program that kind of gets you into blockchain, into the philosophy of blockchain and the ideas of blockchain, more than the technical details, although there are like kind of more technical tracks also, but it's not just for technical people at all. It's for anyone that is interested in blockchain. And then I did a hackathon. That was kind of my first contact with zero knowledge proof, that I was like very lucky to join the team of one of the experts in ZKP, that is Wei Ye from Singapore, that worked at the time in PSC. Then I got like a grant from the Ethereum Foundation, the Ethereum Protocol Fellowship, and I worked there in kind of consensus protocol layer, mainly in Prism, but in other things as well. Yeah, it's super awesome to be able to work also in public goods and in open source software. So that's really. And then I kind of got this amazing job at the ZKVM team, that is part of the PSC, that is part of the Ethereum Foundation. And that is like, basically we're trying to build a zero knowledge proof for every block in the L1 Ethereum. So it's different from other ZK EVM projects that are more like focused on rollups. We are focused more on kind of being able to prove the L1 blocks, all of them, including the one that had proof of work, and including kind of all the hashes that are not designed for ZKP, that are in the EVM, etc., etc. It's a really amazing project, and I met like people that are really super smart there. And I'm very happy about that. So what is kind of like my my perspective about the, I don't know if this is really clearly my perspective about how is kind of currently the ZKP world, no? Like there is some academic work being done all the time with a lot of innovation, and some kind of genius is able to create proof systems from that academic work, kind of like very bravely and very hardly kind of make it work into a proof system. And there are like super smart people that are able from those proof system on top of those creating some ZKP circuits. Are really smart people, but the problem is like there is a disconnection with like idiots like me, like the average programmer, that you need to kind of solve if we want to get to kind of the infinite garden of ZKP, you know, because like we need like a lot of more people working on ZKP projects, especially these huge ZKP projects like the ZKVM that require a lot of resources and a lot of effort, no? And there is like kind of a barrier for that. And that's like what is the why of what I have built. And then first I'm going to talk a bit about the why, and then talking more about the what. So kind of like for this problem of kind of how to get like average programmer to contribute in ZKP circuit, perhaps there are like kind of two ways of solving it. Like one, like that is like Chiquito is working on, and we're working on the residency in Vietnam. That like we could perhaps like get to implement a ZKVM for a general purpose architecture, like the ZKWASM, and then we could just compile stuff to ZKWASM and prove it, and just compile it with the standard compiler and have all the tooling for the ZKWASM. And I mean, it's difficult to make this like into very efficient proofs. Yeah, we don't know like if it will be useful for all problems, or we will need something else. And that's like the other solution is to create like better and higher level tools to implement ZKP. And that's what I'm talking about in this presentation. So like the ideal situation in that case is kind of shouldn't end in proof systems, no? And like some super genius people on top of proof system being able to create some ZKP applications. No, there should be like a language that is more abstract and higher level than the proof system. There should be libraries, tools, and then on top of that, you can start building applications and having people building applications. So and this is kind of inevitable, no? So the project I'm working on, the ZKVM, started kind of trying to build this ZKVM on top of Halo 2. That is a proof system, a Plonkish proof system, and kind of it was inevitable that we needed to create a lot of abstractions on top of Halo 2, on top of Plonkish, to be able to build the ZKVM. Without these kind of abstractions, it would be kind of impossible to build something of such complexity just right away on top of the proof system. So that's like what is Chiquito Pecador Plonkish. So it's like kind of a higher level abstraction that seems like most of the abstraction that we are using already in the ZKVM. So I think that's very interesting because the ideas that we are implementing in Chiquito come from actually a real use case and have emerged naturally from it. So they are like abstractions that we know already that are useful, no? And then we have like a working prototype that has implemented one of the circuits of the ZKVM. I think one of the 8 circuits of the ZKVM is kind of like the 50% of the circuits that are simpler, that is easier. It has a DSL in front of the language built on Rust and a backend in Halo 2, and can compose with other Halo 2 circuits. I had to do this so it could work with the rest of the ZKVM. So it's implemented in a way like we could introduce it step by step, and probably that hopefully that will happen into the ZKVM. No? So some circuits we will build in Chiquito, and some circuits that we will not be able to port them to Chiquito, they will still kind of be able to work all together in the ZKVM. So let's think. I don't know if this is very readable. Yeah, because of the code. Probably should have chosen another color scheme. So I don't know. Can you see it more or less the code here? No, it's really bad. No, I don't know if I could do something. Yes. So this is how it is. So the one in the middle, it's how it is implemented now. So it looks like there is like already. I don't know what's happening. I need to press a button. So the one in the middle is going. Perhaps the cable is not well inserted. Okay, let's hope. It's again. The one in the middle is how implemented now. So it's kind of there already like this. Some of the, you can see here some of the abstraction that we kind of have implemented ad hoc during the ZKVM development. Here, like the constraint builder, and there are kind of some abstraction of some ideas that are not abstract out, that are kind of have to be done manually. If we kind of back translate that into pure Halo 2, this is what it results. No, there is this huge. Perhaps if I put this, let's see. There is this huge expression. There is this huge expression with a lot of boilerplate code. I can share them. So I can share them.
Share the Zoom link in our chat. Open it, and then you'll see the screen.
I can share also the slides. Yeah. Views, then copy link. Okay, so I'm going to put them in information. One moment, please. Yeah. One moment, please. Yeah. Let me put it in information. So I'm going to put it in the information channel. Okay. So I put the slides in the information channel, and let's now close Telegram. Done. Allow accessory. Allow. Doesn't it gets allow? Yeah, no, it doesn't. Well, it's working, no? I don't know. I want to press don't allow, but it's going to be always there. Oh my God. This must be a bug in allow. Now. Okay. Allow. Okay. Let's hope this works better. Yeah. So yes, say like I kind of back translate that to the expression, the normal Halo 2 expression. Yeah. And this like all results in this kind of impenetrable code. Well, sorry, I lost a bit the track with all these technical details. So what I was going to say, yeah. So, and this is just one kind of 30 rules that are in this circuit. That is one of 10 circuits, and it's not even the more complex. Okay. So it's impossible that we build something this complex with this kind of like just like on top of the proof system. No, these abstractions that I'm talking about are kind of inevitable. No? Like if you want to build something this complex. And this is like here below, you can see how it looks in Chiquito. Okay, so this circuit, the whole circuit, I can show you later, has been converted to Chiquito and passed the tests. Yeah, and it's like this is like because not only we have made like the way of writing the constraints like kind of more nice to see, like nicer, in the syntax, but also there are some of the things that are there that has been abstract out below. So you don't need to write them. They're kind of automatic, like this thing about the queue enable and queue last and all that, yeah. And that's like how it's built, has been built in a kind of really following a software engineer kind of approach to, it's the same, yeah. To this type of thing. Perhaps my version of man has some bug or something, I don't know. Perhaps it's Zoom or something, I don't know. So so there is a DSL that currently is created in Rust, and that converts to an abstract syntax tree. That kind of like, it's like a data structure that contains the intention of the developer of what it says in the DSL. And that's compiled to an intermediate representation that is a Plonkish intermediate representation, and thus is translated into Halo 2. Okay. So yeah, it seems like I have to press like a button time to time. So actually this enables, for example, we could build like a DSL in Python. That's something that many people at the residency requested. So with this DSL in Python could translate to the same abstract system tree, and then the rest of the process would work already. So be like a small job. It wouldn't be like you need to rewrite everything at all. And then, for example, we could put other Plonkish kind of like Sangria or Plonky 2 at the back of the translate from the intermediate representation, and also be like a simpler task. So the advantages, it's like kind of like, as it's clear, like it's easy to read, it's easy to learn and to teach, So we can get more developers into ZKP, and it kind of abstracts out a lot of complexity. So it's more difficult to make mistakes, and it's faster to code. So that's I think is what we need. So it enables us to have like a CK infinite garden and start seeing like all the time applications, real applications popping up and startups popping up that are building on top of these technologies. So the idea is like be kind of as simple as install like in the end like a package, and you could start like building CKP projects. I'm going to explain. Now, this is kind of the reason about why I built Chiquito, and this is kind of, I'm going to dive more into a technical explanation of how it works and what it does. Yeah. So this is, what is the Plonkish, like who doesn't know like the Plonkish arithmetization that is different from R1CS? Who doesn't know that? Okay, that what is the Plonkish arithmetization? Okay, so the Plonkish arithmetization in some ways is kind of a more flexible arithmetization that R1CS, that you only can have like many polynomials of degree 1. And so in the Plonkish arithmetization there are like columns and rows. So it's kind of like, you can think about like almost like a Excel spreadsheet, okay? And the public input, the witness, like the private input, and also like these things called fixed data, fixed columns, are all going to be there in the cells of this table, okay? And they are all going to be numbers in the prime field of the prover. Okay, and then you can build constraints that are kind of arbitrary polynomial constraints, and has like rotations that are this kind of relative conversion. So this relative kind of expression. So for example, here we have A plus B minus rotation of D3 equals 0. Well, what you can, it came back. Yeah, it's like, oh my God, it's like a conspiracy. Perhaps it's like when like the TV doesn't work and you need to get closer and you try to move the antennas like in old times. Okay, so you can see like the A and B is kind of like rotation 0. Okay, so you can see them as like there is a rotation A 0, rotation B 0, and there is rotation D3. equals 0. So what this means is like a plus b is going to be equal to the 3 rows below. No? So if the first one row is the 0, then 1, 2, 3, and that position of the d has to be equal to a plus b. And this has to be true for all the rows, and it kind of goes around. So when it gets to the end of the table, goes around the rotations. That's why it's called rotations. And that's how you express the logic of what you want to prove. Okay? And then in those columns, you can put some columns are public input, some columns are kind of private input witness, and some columns are fixed. Like in the setup, they're fixed with fixed values. So that's kind of like the basic 3 types of columns. Then there is something else called lookups. So you can create vectors of expressions that have to match vector of expressions in any column. So the source is in one column, in one position, in one row, but then it has to match in any row that expression. That's more difficult to understand. I mean, I need more tools to kind of explain it. And then there is something else called copy constraint, that basically you say that this cell has to be the same as this other cell. And that's kind of basically the tools you want to build. If you want to build like a Plonkish arithmetization of a zero knowledge proof, that's the tools that you kind of have, you know, like these tools. And you can have many rows, many columns, many rows. Of course, the performance depends on the number of columns, the number of rows, the bigger rotation in the whole constraints. No, like this is not. There is not only one. There can be many of these constraints, many of these lookups, many of these copy constraints, and so there are like many factors that affect the performance. No. So it's like someone has a question about the Plonkish arithmetization. I don't know if I explained it very well. It's yeah. So basically, yeah. Example that is very easy to do is like the Fibonacci sequence with Plonkish arithmetization, that you can have like 2 columns or 3 columns and say, okay, C has to be A plus B, but then the C has to be equal to next A. So then, and then you keep adding and you can go like, and then this rule has to be true for all the rows, no? But also you can have columns that activates constraints. So if you multiply one column for the whole constraint, only if that column is 1, that constraint is going to matter. If it's 0, then that constraint is kind of deactivated for that position. No? So that's like kind of what we call a selector. But on top of that, like we had to create other abstraction if we wanted to build the ZKVM circuit. No? For example, like talking here about the cell manager, the step selector. No, like we have. One thing that the Plonkish circuit is good, like when you need to kind of do something in sequence for a sequence of things. No, you can use different rows. No, you can have like in the Fibonacci example. No, you can have. Have like a list, no, like a laundry list of things you need to check, no. But if we have like so complicated operations that they change in the complexity and in the amount of witness that they need. Okay, so yeah, I just realized I just need to approach the thing. Perhaps if I stay here. So so the idea is like basically, yeah. So we need like these laundry lists of operation. Okay, sometimes have like different complexity, and you cannot, if you use one row for each of them, you are going to be like misusing like many columns, because like the biggest one is going to kind of enforce you the number of columns that you need. So what we do is we created something called the cell manager that kind of take like kind of what I call a super row, so a section of the Plonkish table, and say this number of rows kind of have a meaning, and then abstract out from the set of constraints that we are going to apply to this super row, abstract out getting each of the cells That's why it's called cell manager. So if a set of rules need like for if a set of rules needs for signals, then in this case with 2 columns is going to use 2 rows, and if another needs 6 is going to use 3 rows, and each of these rows kind of execute what we call like a constraint, what we call a step, no? And then there are different step types, and those step types use a different number of cells, and the cell manager extract that, as I was saying, no? And then there is like these super rows are used for different step instance. So the same step type can be is instanced many times in the witness. So each step type has a series of constraints, and then there is selectors that kind of activates them. So we can see here, no, we have like C1 and C2 are kind of more like pure witness columns, and S1 and S2 are used to select between the 2 types of steps. So when this is 1, because all the constraints of the step type 2 are multiplied by S2, is going to be activated, the constraint of the step type 2, and because this is 1, because all the rules of the step type 1 are multiplied by S1, the constraints are going to be activated for this space. And the next kind of thinking leap is like you want actually to share information between the steps, because you need to constrain the like kind of the transition between the step and make sure that they follow some logic. And there's like these cells that we have in red are kind of like the same meaning in all of them, and they are always aligned with the same alignment from the beginning of the super row. So the A is always in C1 and rotation 0 from the beginning of the super row. B is always C2 0, and C is always C1 1, rotation 1. Okay, so these kind of common cells that we will call kind of forward signals, because when we are constraining one step type, we know the height, the number of rows, because the cell manager calculated for us that we're going to need. We can just add the number of rows to the position of A to get to the next A. So we can create constraints in this step type between the rules for this step type and the values of A, B, and C in the next step type. So basically, for the developer, like the abstraction that Chiquito does for the developer, okay. So in the instance, so in this example, there are like 2 step types: step type 2 and step type 1. And from the point of view of the developer, they just like in sequence. And there is this share kind of signals that are A, B, and C that you can check the next one. For A, B, and C, you can check the next one. And then there is these internal signals, RTV, that are kind of not transparent between step types, no? So, and then we have placed here like step 2, the first row is an instant of the first super row, no? Because this is an abstraction on top of flunkies, no? Behind this is happening, but the developer only have to think at this level, no? I don't know if this is clear. I can go on this abstraction. Yes. Reason? Reason. What do you mean by reason? A region. Region. No, yeah, the region is something about Halo 2 for the layouter. That's abstract out from the developer. But yes, these will be in the same region in Halo 2. Yeah. Yeah. Yes, yes. So the user thinks in these terms. The user of Chiquito thinks in what I'm showing now. So there is like these super rows. Yeah. So each step instant is one place, and you can connect it with A, B, and C, but not with the other ones, because you don't know if the next one has like D or not. And this is what really is compiling to. But the user doesn't know, that doesn't need to think about this. That's precisely the help we are providing them. Yeah. Yes. Yeah, like signals. Yeah, internal signals. So these are RTB are internal signals. So each step type. So the step type 2 has the internal signal RTB, and the step type 1 has the internal signal D. And then they all share A, B, and C, and each of them has like one A and C, but the difference is like A, B, and C, because they are shared, I can see the next one. I can constrain on the next one, of the next one of the next instance of the next part of the witness. Yeah. Yeah, I will show the code later. Yeah, I will show it in code. Yeah, yeah, but I'm trying to. Yeah, yeah.
Is that 2 instances or so, 1 instance?
Yes. No, there are 2 step types. So it's a step type 2 instance, a step type 1 instance. So it's like classes and objects. There are like two step types. There are like 2 classes of steps.
Classes?
Yeah, like in object-oriented programming. In object-oriented programming, you have classes and objects. Okay, so here you have step types and step instances. Okay, so yeah, let's try to go something. Yeah, so sorry. So a step. I think explain it here better. Yeah. So in this kind of example circuit, no. So we have like a circuit. Okay, has the forward signal. So in this case, forward A, B, and C. Okay, and then we define step type 1. Okay, and this one has like the internal signal D. No, I think it's in the example. No, and then they have like constraints that involve A, B, C, and D. Okay, and we have a transition constraints that involve A, B, C, D, and next of A and ABC, but not D. D doesn't have next. We cannot do next.
Step means these like transitions. So different step types means different transition function. Right?
Yeah. So a step type is like a transition function. Yeah. Like depends. I mean, you can use it for different things, but yes, you can use it for kind of like an opcode can be a step type. No, if you are, for example, we create a VM, no, it can be like an opcode can be a step type. But yeah, but you can use it for other things that are not opcodes. Yeah, like we don't use it only for in ZKVM. We don't only use it for opcodes. We use it for example, in the if you are implementing the hash, the keycac, the SHA-256, there are like these. You do these rounds. So a step instant can be 1 round of keycac, and step types are different types of rounds. Yeah. So it can be opcodes and things like that. Yeah. So then you have a step type 2. Yes, just to finish, no? And then when you are creating the witness, when you are doing the witness generation, okay, you say, okay, I add a step 2, then with different data, step 1 with different data, another step 2 with different data, and they are all put, no?
It's a trace.
Yes, like a trace. If I actually using that word, yeah, it's a global secret. Yeah, yeah. Sorry. Okay, so we, well, yeah. Thank you. Open cap. Okay. So yeah, so this is what I explained now again, no? So each the secrets are the first signal, the step, then the transition constraints, the transition, and then the witness generation for each for one instant is the code is encapsulated in the step type, and then the trace is kind of calls different step types. Yes.
Forward signals mean that the signals that don't change.
They change. No, they are not fixed. No, the forward signal is like you can check the next one. So the forward signals, the difference with internal signal, you can check the next one. So this step can constrain about the A signal in the next step.
Forward means
Yeah, like can look forward. Yeah.
Look for, okay.
Yeah, forward like can look forward. Yeah.
Next line.
Yeah, next line. Yeah. Yeah, yes, you can use in the correct constant the next line. Yes, yes. And that's done because like for each step type, when you convert it to this, you know the height. So you can add the height. So A, because A is in the same relative position, you can just add 2 and then you get to this A, and this can add 3 and then gets to the next A. Yeah. Yeah. Awesome. So we have it like so this is kind of easier to understand a circuit that is written in the original way. Yeah. So ideas for this hackathon about Chiquito that I want to kind of introduce you is like perhaps your project implement your project using Chiquito. Well, kind of a warning. This is alpha. So implemented this like last month. And everyone must to know like now my colleagues are reviewing it to see if we put it in the PSC repository. But now it's in my personal repository. And yeah, this is very early stage. So, but yeah, it passed the tests. It passed the tests. Yeah. It passed the tests of one circuit. So to test it, I converted one circuit of the ZKVM to Chiquito, and it passed the tests. So perhaps if you are interested, perhaps this can work for your project. I don't know, depending on your project, and I will help you. And perhaps we find out that we need to improve things in Chiquito to make your project work, and that's great. One thing we can do if you don't have like a clear idea, but you'd like to use Chiquito, perhaps like implement MinC or Poseidon other hash in Chiquito, and that could help for documentation for the future of Chiquito and such. The CK memory on Chiquito, no? So Chiro is going to present the CK memory project. So perhaps we could implement that on Chiquito. I don't know if it's possible or not yet, but there's something to research. And other example circuits, if you want to kind of try Chiquito, perhaps like some simple circuits that we can use them later as example. So for the documentation, no? Because there is no documentation yet, I just building, no? And now another project, because this is like, of course, like a common goods open source project. So like other project are also kind of having pull requests and your name on commits in open source project kind of helping me a lot in my career, no? So that's also interesting for people. So something that many people in Vietnam requested, like could be super cool, is to add Python. So they would love to be able to write circuits in Python and then connect it to Chiquito. So kind of like the same ideas, but in Python. So they were kind of like creating a DSL in Python and then convert it to the abstract syntax tree of Chiquito. Adding a backend for other Plonkish proof systems like Sangria or Plonky2. So be like kind of take the intermediate representation of Chiquito and convert it to these systems. Helping with logo or the marketing of kind of like the brand of Chiquito. Documentation, like for Chiquito, more proving that is cell manager aware. So it's very interesting. Like we are using the cell manager, but we have these columns that are basically shared between different ideas, and the mock prover of Halo 2 cannot handle that because doesn't understand that. It tells you the name of the columns, but because we're using the cell manager, doesn't help so much. So be super cool to have like a mock prover that can tell you, have the information about the correspondence between the cells and the signals. That's a very interesting technical project, no? That helps you understand how circuits are built, reviewing code or something like that, and adding features to Chiquito. For example, lookup as a call is another abstraction that we are kind of using. It would be very interesting to have like a feature in Chiquito. And there's like questions and feedback. Oh, yeah. Okay. This guy is Chiquito. He's Chiquito. He's a Spanish comedian. We were like a bunch of Spanish people in Vietnam, and kind of like to start kind of talking about this, like I called it Chiquito because I know it was going to be funny for them, because it's this comedian that passed, that was super famous because it was very weird and surrealistic, and yeah, I was called, his kind of artistic name was Chiquito. Yeah. Yes. So yes. So we can, I mean, if you want, I can go over the bytecode circuit in Chiquito. And I can explain, I mean, I don't know how much time do we have, or? Okay, if you are cool with it, I can explain one of the circuits of ZKVM and explain how, and show you the code in Chiquito, and perhaps show you also the code how it's implemented right now. Okay, so. Yes, so there is the bytecode circuit. So it's a circuit basically to check, to prove that the okay, it's like the sharing of the screen is in a different window. So I'm going to share, new share. Yeah, this one. So I'm going to change what I share. Yeah, so it's like yeah. But so this is the code. How do I close this? Okay, yeah. So yeah, but the bytecode circuit is a circuit to check that that we have the smart contracts, or like all the bytecodes of the smart contracts kind of are the right one. So we have like all the bytecodes of the smart contract, and we checked that the hash of those match the hash of the smart contract. So they cannot like we need to be always kind of like worried of a how do you say untrustworthy prover, no? Yeah, dishonest prover. So they could change the smart contract code to pretend that something happened that didn't happen. So we need to kind of check the smart contract code, make the hash that we have, all the opcodes in order match the hash, and check that we have all the opcodes, that we don't have skipped one, that we have them in order. So then the other circuits can work with those bytecodes and make sure that when they are processing like an opcode. So basically, how is that for each smart contract in a block? No, because we need to check the block. So there is like a row or a super row. There is a header. There is a header, and then there is like for each bytecode, there is a byte row. Okay, and then there is again when this ends, there is another header when another smart contract starts, and there is a byte, and they start like each byte. Okay. Yeah, and basically like that. Okay, so for each smart contract that is in the block that we're executing in the block, we have a header, row and then byte rows. And then like the header comes with the hash. The header comes with the hash, the length. Yeah, basically that. I mean, more importantly that. And then each byte has like a value, like the opcode. And then the index. And then the index. So there is like for the first one is 0, and then the next one is 1. And then also for Canva, we need to repeat in all of them the hash and the length to be able to check at the end at the hash. And then we are accumulating a RLC of the opcodes, and then we match with the like then to calculate the hash, no? And then there is like it's a random linear combination. So it's So we use this to kind of accumulate all the bytes and then check the KeyCAC circuit. Yes. So then the last byte is also important, no? Because here we have checked all the bytes, and we will have like a final RLC that then we check like the hash and the RLC. We do a lookup to the KeyCAC table that has done the KeyCAC and then the hash and the RLC should match. Okay, so that way we are then make sure that the hash of the bytecode actually reflects the bytes that are in the bytecode. Okay, and also like the circuit that. So we use like that's what we call like this is kind of like a call to a function, no? So this lookup is almost kind of getting the result of hashing the RLC or hashing the opcode. So that's why we use kind of like lookups as it seems like a similar to a call. So also like if you have like here like the circuits that execute the opcodes, each of them lookups here to match that the opcode, the PC and the PC and the opcode code matches with the value here and the index here. So there is like, okay. So then everyone kind of understand, I mean, you don't need to understand everything, but kind of roughly the idea. We have this circuit to kind of check that all the smart contracts we are going to execute, that we have all the opcodes and they are complete and they match the hash of the smart contract and nobody is lying to us. So, okay. And we have like two step types, the step type header and the step type byte, and kind of the last byte is kind of different. Okay. So we have like so then we have forwards. Okay. So we have like the length is a forward signal. Okay. So each step can check the length of the next step. The push data left is a forward signal. So this is about how the push works in the EVM. I don't want to, and then there is this value RLC that is kind of a way of accumulating the bytes of the opcode to then match with the hash. So like more technical thing, mathematical thing. And then I'm importing some Halu because this works with the other circuits, no? So I'm kind of importing other Halo 2 columns into here. You don't need to do this if you were kind of just creating a code in Chiquito completely, no? But because it's just like a part of a program writing Halo 2, I have to import this, and then I import this, and I import this. It means it's kind of connected in many ways, no? With the other circuit, no? So this is kind of about other circuits can look up into this circuit to check the opcodes. This is kind of to know the push data, how the push works in the EVM, and this is about calculating the hash, the KeyCAC hash of the smart contract, no, like connecting to other circuit, no. So we define here forward signals, kind of imported columns, and then we have two step types, header and byte. And we also, we kind of have here like a pragma that says, okay, the first step has to be a header and the last step has to be a header. Okay, so this in the actual circuit in the old circuit, no, there is like a column that is called Q first, and then there is a column that is called Q last. Okay, and then it's a fixed column, so the values are in the setup, and the Q first, the first row is 1 and the rest is 0, and the Q last, the 0 is the last one, and that way we can enforce things special, like we need to, because the rotations go around, we need to make sure that certain conditions happen, no? So this is the Q first and Q last. So this is abstract out from the user. The user now just to have to say, okay, this is the first step type, and this is the last step type. Okay. There is also a column, there is the Q enable. So because this circuit is like Q enable, yes, sorry, enable. Yeah. The circuit. So this is one for all the rows, because the circuit is sharing the Plonkish table with other circuits, and sometimes they can be one on top of the other. So each circuit has kind of a Q enable that is one for the space that is using from the whole, no, because in the end, like the Plonkish table is full with many circuits to make this work, to make the ZKP work. This is just one part of it. So the Q enable of the bytecode circuit is kind of activated for the part of the table we're using. And that's also abstract from the user, no? So that's created in the background for the user. So then we define the step type header, and then we start at the constraint, no? So for example, the step type header, for security reason, to make it more, the index have to be 0, no? So well, this is a notation, but then we'd say EQ index 0, okay? And then the value has to be equal to the length. This is if another circuit wants to check the length of a smart contract, just has to look up to the header type, to the row with the header type, and the value is the length. So you can change so the hash, I mean the header type, the hash of the smart contract, and then can make sure that the length is like the value. So we only share the value, we don't share the length, but in the header row, the length is the value, so we can know the length. Then there is like, if the next step type is also a header, the length has to be 0. So that's like if the next step is a header, the length has to be a 0. That's why, of course, if the length, if after a header there's a header, that's like an empty contract, no? So that's another constraint. Then if after the header there is another header, it's the empty contract. I mean, it's the same situation. So the hash have to be the empty hash. No, the hash of empty smart contract. No. Now, if the next, we are in the header step. If the next step is a byte step, the length has to be the same. So all of them have to repeat the same length. If the next step is a byte code, it has to be the first one. So the index of the next, this is because it's a forward signal, the index of the next have to be a 0, because the first byte has to be the 0 byte of the smart contract. No? And then it has to be code. This is about the push. I don't want to get into how the push works, but no, but like basically, okay, so perhaps so in the opcodes, no, you have perhaps add or whatever, no, and then there is the type of this type of code that perhaps is push and then the number, like push 3, and then the next 3 bytes is the next 3 bytes is data, okay, and then this so this is kind of so for this is code is 1, no, and for this also is 1. Sorry, 1, it's not 0, 1, yeah. But for these 3 is code is 0, no? Okay. So yeah, to distinguish kind of the data, this is not the case that there are data, no? It's only the only way to kind of push it. Well, no, it's not but basically, yeah. So and then the hash we copy kind of has to be the same, no? All the line has to have the same hash and the same length. And then we kind of start the value RLC thing, the random linear combination that help us to check, but I don't want to get into details, no?
So what is this context that we use?
Yes, so that's like the witness generation of the head, because yes, the witness generation of the header type. Yeah. So this is the witness generation of the header type. So this is like one row of the header. This is only the witness generation of one row. So it gets like a data parameter. And yeah, this is like a Rust technical thing. But then basically we assign tag that marks that is a header to the lookup. We mark it at 0. Index, we assign it to 0. Then the length has to be the length. The value has to be the length. That's something that we constrained here before for the header. No, the value and the length is the same. And then its code is 0. Value RC is 0. And we assign the hash. That has to be. There has to be a trick here because there is something called the challenge API that has to do with creating challenges and all that. So it's kind of like a randomness that is added. Yeah, I don't want to get into the technical details, but basically you kind of has encapsulated how you set the values of one row here. Okay, and then we go to the step type bytes. No, okay. So we have here two internal signals. That's the push data size and push data left. And that's also about this thing about the data bytes. And then we constrain that is so we constrain that is code is the same as that push data left is 0. So if we're in a is code row, in a row that is not data, then there is no data left. No, so it's kind of how we make sure about the data, and then we kind of do a lookup that can be more abstract out yet, but we do a lookup to get like to get what is the for this opcode, what is the size of the data that goes after. So for push 3 is a 3, for push 4 is a 4, and for the rest is 0 for the rest of the, and that kind of is another table that we have. It's a fixed table. I can show you. It's also in Chiquito, that table. And if you interrupt me, something is, or you want to go more detail, and then if we go to the next, if the next row is a byte, the length has to be the same. No, if the next row is a byte, the index has to be incremented by 1. So they are all the bytecodes in one after the other, and then the hash is also copied. No, so the length and the hash is also copied, and then we keep accumulating. This is how we accumulate this RLC that helps you check the hash later. And then if the next step is a byte, yeah, so this is the one that I put in the example before was this. So imagine that this like how we have seen the side of this code. So if this very long hello expression was just for this step, no? So if after the byte goes another byte, if we are in a code, the push data left of the next row is the size of the data of the current row. So if we are in a push 3, the next row has like 3 push data left. If we are in the next row has 0 push data left because it's code, and then that matches that is code.
Past the screen. I mean, there are equations in the screen. You need to have a password to understand what.
No. So the constraint is taken from here. This is kind of like a comment for the debugger. But in the future, I want to kind of generate this string from this. And I mean, it's trivial to do it, but I haven't implemented that I can create this. But yeah, but actually the constraint is this. Yeah. But actually, it's not an idea like to implement a parser from the text. I haven't thought about that. You just need to, yeah, because if you are given like names to the string names to the signals, perhaps you can do that. Yeah, that's a good, yeah.
So it seems to me,
Yeah. It's based on Plonkies, yeah, yeah.
So I'm wondering if you could put like for example, where they try to like aspects of power, they try to remove that knowledge of the underlying previous system. You see, like, and there was a slide you had
Yeah.
beforehand where you showed like how it goes from this today.
Yeah. Yeah.
I'm wondering, you see, like, are you talking about Python device? But I'm wondering if you see like a layer above all this that would be that might use Chiquito, or do you think this is like more of like
I think this is higher level than what there is. Yeah.
it's higher level what there is, but I'm just thinking like in terms of like to build on top of that. This is still quite complex in terms
Yeah.
of the day-to-day
Yeah.
programming experience here.
Yeah.
Whereas when I look at something like one, that feels more like I'm just writing a plus function.
Yeah. I think this is still lower level. Like it doesn't have into account. It's more like Circom, no?
Yeah.
Like Noir. And I think that's lower level because this concept of the steps and that you don't have it. So what is I'm elevating is going up the concept of the steps that we are using so much.
Would you see this as like a compiled target, or go one step lower and if you were building something that was a bit more sort of, yeah.
So my idea is to add more abstraction to this, but more than on top of this, like in parallel, like the call as a lookup, no? So perhaps like define like lookups in a more clear way. Well, in the anyway, I think there is like kind of a progression in the programming system as going higher level. So I think we are going a higher level step here. I think, yeah, perhaps we cannot imagine yet how a higher level, perhaps Turbo Chiquito or Chiquito plus plus would be, no? But perhaps, yeah, of course, you can go higher level. But I'm trying to get to a level that we don't lose performance with respect to Plonkish. So it's kind of as close as Plonkish, so we can build circuits that are basically how you write them in Plonkish directly, but with some abstraction that there are some things that you don't have to care about. Yeah. So I don't know about the future. I don't know how they will go. Perhaps like the CKVMs get so good that we don't need to write circuit manually anymore, or we need to go higher level in these abstractions, and then compile to this. Yeah. So it's interesting question, but I think still this is higher level that Circom or Noir or the PLL is in the polynomial identity language, in some ways have some more stuff. It's still kind of like lower level how you describe things, but has like this ROM, and there is like some added ideas that are similar to this, no? So yeah. Yeah, yeah. So I think I'm making it easier because the constraint builder, how the constraint is written, are easier than in the other implementations of Halo 2, and then I'm adding the abstraction of the steps, and that's higher level too. Yeah. But yeah, there is yeah. Yeah, we still need to keep it, and I think there is also a bit of the Plonkish way of thinking of having like a list, like having rows. So I create this abstraction of the super rows, so you don't have to think like there is like the actual rows, and then there is super rows that take several rows, and then you don't have to worry about the allocation. It's kind of like there is an allocator. The cell manager is kind of an allocator of memory, but for rows. Sure, no problem. Yeah. Yeah. Yeah, like in Plonkish, below is converted into gates. Yeah. So sorry, could you repeat the compare? Yeah, I think like people are thinking about this, and I don't think like there is an easy way to compare complexity across proof systems. Chiro knows much more than me about the proof systems. I'm more like a secret, but I think like yeah, nobody like it's like comparing like CPUs, no? Like you can always change the benchmarks and yeah, my understanding is kind of like there are like two categories: the ones that are more like L1 CS and the Plonkish, no? That kind of like in general know how do you make like categorization of the Plonkish, huh? Yeah. Yes. So of course, like the number of gates affects like the degree of the gate, like the degree of the polynomial constraint, the number of rows, the number of columns, the biggest rotation. Like I learned from my colleagues working on project system that in Plonkish, at least in Halo 2, the biggest rotation you put in the constraints kind of also affects the performance. Yeah. And then, but yeah, but it's not like they tell you, no, this is the formula for no. Apparently, there is no such thing, or they don't know it, or it's too complicated to work out. Yeah. Yes. Yeah.
Yeah, that was kind of this question also is like, what is exactly being gained or lost by moving up the abstract?
Yes. I'm pretty sure that in Chiquito we are not losing from the way we are writing the circuits in CKVM, we are not losing performance. It hasn't go high enough in the level of abstraction like to make you lose performance. No? And I think you could always, like in the same way you can inline assembly in C, you could leave gates open for specific things to be able to kind of do it at the lower level for specific things that get more complicated or get like more harder. I think that probably will be the future. No, like yeah, like you can combine level of abstraction in a programming. Then if you're worried about if you're worried about performance, sometimes you profile them and I think yeah there will be I think in the future we need to build profilers and things like that for CK, and that tells you okay, this is like the problem is here, like this part is making the proving time worse, or the memory requirements, because it's also like another bottleneck, no? Like how many, like the CKVM needs like terabytes of RAM, like the one we're building, no? to calculate. So with the RAM. Sorry? Yeah. Yeah, but we're not focusing on this kind of thing because we want to prove like L1 blocks, and it's different, and we're not focusing on we collaborate with Scroll, and they are also testing hardware acceleration. Yes. But yes, and there are also like so many new proving system like Nova, Supernova that promises a lot, like about how to make like much less memory and better time. Yeah, so yeah, folding scheme is Supernova has a folding scheme. Yeah. You should talk with Chiro about that. He knows a lot about that. It's really tough. I don't know much about the province system, really, how they work, lower level. So I was writing circuit as a software engineer, like thinking how we can make this easier for software engineers, kind of, yeah. Yeah, I don't know if you want me to continue. I mean, I think here we have like the witness generation for the byte step. And then this is like the trace, no? So you basically call this CTX add to add a header for each byte code. You add the header and then you add each of the bytes. And that basically calls the witness generation of each row for each instance of the step type. Okay. Huh? EVM what? Sorry? Byte code. What is the byte code? The byte code is like the operations of the smart contract, like the smart contract. It's like the machine code. Yes. No, this is the DSL. This is the DSL. Yes, this is the DSL. So this is like kind of the front end. Yeah, this is the. So what you're seeing is like the code written in the DSL. So this is a Rust DSL. How do you constrain? What is the verb? How you build the AR? How do you? Okay, so I can show you the code. No, there is no CKVM there. This is to write circuits, ZKP circuits. Yeah. So this code is converted to Hello 2 circuits. Yeah, this is one of the components. So this code is one of the components of the ZKVM. Not that it runs on the ZKVM. It's like one of the components of the ZKVM. Yeah. So no, but it can. This is the no. This is
Context actually is
the. No, that's part of the. That's part of still of the. That's still part of the DSL, the CTX. Yeah, actually, what it gets kind of. That's like data structure that you don't see. So you just write the DSL, and then the code. I can show you like if we want to go deeper, I can go deeper. Let me stop share screen, or let me no. One moment, yeah. Let me show you file. Open recent Chiquito. Okay. Was here. This. So what is the Zoom? Share screen. Here, okay. Share. Okay. Can you see this perhaps? So this is the DSL. This is the DSL. So this is like the function we call when we define circuit, and we pass it like a lambda, or like a lambda. That's def, and then this code kind of start building the abstract syntax tree, and the abstract syntax tree is like structure. No, there is a circuit that has the forward signals. These are imported Hello 2 signals. These are a map with the hash map with the step types, the trace function, the fixed column generation. That's for another circuit to have that. The annotations are here. So it's an abstract data structure that kind of represents what the user says to the DSL. So when the user says forward, no, ctx.forward, basically to the circuit, to the abstract syntax tree, add a forward. Okay, so it's start building the. That's more advanced. Like then there is an intermediate representation. So this is the backend. So if you want to see here, this is the backend. So it calls create gate, and then this is. I don't understand. How to center synthesis. Yeah. So this is here. This is here. Here is the hello2 configure, and here is the synthesize. Okay, synthesize here. Yeah, but that's like that's in the perhaps I should share the whole thing, the whole screen, because yeah, desktop one, yeah, the whole screen, because I'm trying. So this is done here in this step. Okay, this is the last step. That's the last step. Okay, that's the last step that comes from the intermediate representation that is here in the compiler. Yeah, so there is a intermediate representation that is like a compiled circuit. And the compiled circuit basically have columns and polynomials, okay, and lookups. And then from this data, basically this data is the intermediate representation, this step. So this basically what does Chiquito. This what you're asking is what it does. It's the code of Chiquito. So you can check the code of Chiquito. That's right. Yes. So you need to write. I can send you later. So I need to kind of change some code to write like some print ln so it printed that's like a printout. I can send around like the abstract syntax tree and the intermediate representation. I can send you like a dump. Yeah. But I need like, or because I need to, yeah, I need to perhaps we have it here. Perhaps we go here, circuit, blah, blah, blah. Perhaps I can do it now. Let's try. Bytecode Chiquito, okay. So bytecode Chiquito, yeah. So compile bytecode Chiquito. Okay, so if I do a print ln thing is yeah of the bytecode circuit, okay, and then I do here, for example, let compile equal compiled. And I need to return compiled, but before I print it. Okay, print. Yeah. Okay, so now I'm going to run a test and I hope it will print out in the screen. Okay. So okay, let's run this test. Okay. This just does one pass, I think, no? Yeah, this only does one test. So it's going to print once only. Run test. I hope I have saved this file. Okay, so now it has like, this is the, was like a bit, yeah. No, I think that's the, it's like, it doesn't fit in the screen. I don't know how to, set up the terminal change color, toggle size to content width. There is a way to, yeah, this is basically this is the AST. This is AST, like for example, transition constraint inside a step. Transition constraint have the annotation and then the expression. Okay. And then another transition constraint with the notation, the expression. So they still basically have like what we have said in the DSL, but just in a data structure. And then the ER is, I think, start here, yeah. So the ER, no, because it's contained. It's like the ER still contains the steps for the witness generation that is done at the end. So it needs to give like a lot of information. But basically, the main important thing of the, like for example, the step placement that have like kind of for a step, for one step tells you where the internal signals are. So the push data size and the push data invite, the step placement is part of the generated by the cell manager. Have placed it in this column that has ID 8 and rotation 0, and 28 and 27. Okay. And then these are the list of the columns in the intermediate representation. So this like the columns and more columns. Yeah, that's the color of the, yeah, that's the columns created by the cell manager. These are all the columns, okay, that we have generated in the intermediate representation. And at some point, I hope it start the polynomials, and then start the polynomials. So this is like one constraint. What we can see here, for example, is that there is all multiplied by Q-enable automatically, and it's all multiplied by the step selector of the for header. Yeah, and then, yeah, I don't know, I don't want to go to my detail, but yeah, if someone is, I think it's better, no, if someone is want to go to all the details, like I am available for sure. Yeah, I don't want to. So let's put Chiquito again in the screen. Something else? Okay. Thank you. Okay, thank you very much. Closing down, then the stop share. I passed you the microphone, perhaps. Thank you.